Alright, this is 3-3, factoring with a leading coefficient. So we're continuing our unit on how a bunch of different ways that we use to solve quadratics. In other words, find where quadratics cross the x-axis. So this is going to be a little bit similar to what we did last time with just factoring. But this time we're adding in the mix of the leading coefficient. So we're going to learn how to factor when there's a leading coefficient and kind of what that means for solving quadratics. So just a really quick reminder, we have a binomial multiplication here. Both of them have coefficients here. And this is just, okay, so hopefully you remember how to distribute. We're just going to distribute quickly. That gives us 6x squared plus 15x minus 2x minus 5. And then we combine like terms in the middle and we get a 13x in the middle. It's a 5 plus 6x squared. So this does not follow the pattern that we learned last time. So remember how we were finding how to factor things by finding things that multiply to the end number and add to the middle number. But notice that this one stops following that pattern. And it's because of these numbers in front of the x's. They sort of mess up our whole deal. And so we sort of have to learn to work around those leading coefficients when we're factoring, because our pattern gets kind of messed up, and so we need to learn how it affects the pattern specifically and how we can still factor when there is a leading coefficient. So factoring with a leading coefficient, you can use this method. So this is sort of a long explanation, it'll make more sense later, but it says we can use this method whenever a is not 1 after you pull out the GCF. So that means there is a leading coefficient, and there are factors of, we're going to fill this in, a times c that add to b. So that might sound familiar from when we were factoring. That one we can use when there are factors of just c that add to b. This time we've mixed in that leading coefficient of a. Hang on, let's pick a color scheme here. A times c that add to b. So just a reminder that a, b, and c come from, I'll do that over here. A, b, and c come from the first, second, and third coefficients in a quadratic. So it's ax squared plus bx plus c. So that's where those are coming from, a, b, and c. So we're going to just follow the steps on the left and factor this quadratic on the right as we go. So first we're just going to identify a, b, and c really quickly. It's always a good thing to practice. A is 3. B is 8, and C is 5. So the first step here says to move everything to one side so that it's equal to 0. It's already equal to 0, so we already did that, check. Then it says factor out the greatest common factor. 8, 3, and 5 don't have anything in common, so that doesn't help us at all. That doesn't have a greatest common factor. The next step says multiply your a and c value and start making a list of factor pairs for that product. So a and c, so we're trying to multiply a times c. So our a and our c are 3 and 5, which make this 15. The product is 15. So we need factor pairs for 15. So things that pairs of numbers that multiply to be 15. So you might find this familiar from what we were doing last time. 1 and 15 work, 3 and 5 work, and I think that's all. Those are the only factor pairs that work. So now we have our full list. The next step says once you find a factor pair that not only multiplies to the c value but also adds to your b value, stop, you found it. So this is a typo. It should be a times c here. There you go. Your a times c value, but also adds to your b value, stop. So we, instead of finding the factor pairs for just the c value, we now are finding factor pairs for the a times c. So it's the leading coefficient times c, but they still do have to add to b. So this is the only pair of numbers that adds to 8, which is our b value. So that's our pair of numbers. And this is the part where it kind of diverges even more from what we were doing. We make a pair of parentheses, which I suppose we're used to, and then here's where it gets weird. Okay, let's read the instructions. Right, 2 binomials with your a value as a coefficient to both x's. So what that means is we are using our a value for both of, I'm trying to do colors good because it helps. For both binomials, we need that number in front of, hang on, sorry. Sometimes I can't talk and think at the same time. So both of those, we need that leading coefficient. Normally, so last time we just had x's. This time we have now 3x because of that leading coefficient. The other place that we put that, so what we're doing here is we're kind of just using this pattern as a tool to factor this. This is my favorite method of factoring with a leading coefficient. There are other ways. I just think this one is the most similar to what we're used to. It's the topic of much debate among other math teachers, but I like this method the best. So essentially we are still just putting the numbers we found in 2 binomials, but instead of just having x, we have 3x because we're putting our a value there. And the other thing that we're doing here is because we put it in both places, because we put the 3 both here and here, if we were to multiply these two things, we would get 9x squared, not 6x squared. So we have sort of an extra 3 going on. The reason that we put it in both places is because we don't know where it should go. So we just compensate for that by putting this 3 down here because we need 1 less 3 than we have. And you'll see how that plays out in a second. But this is just going to fix this problem that is giving us a 9x squared instead of a 6x squared. We just have an extra 3. So we put it down beneath there so that it will cancel out eventually. There you go. Okay, so now what we do is we figure out where that 3 is supposed to go. So we look at these 2 binomials and we ask ourselves, which one of them has something I could factor out? Which of the 2 numbers has something in common so that I can pull it out of my binomial? So you might have noticed that this binomial here, both of them have a 3, which means that we could pull a 3 out of this binomial, which is what we want. We want to be able to pull enough things out so that this 3 will cancel. So we're going to do that. We're going to factor out that 3. Again, this is like that reverse distribution thing that we did with GCF. We did the opposite of distributing. We pulled the 3 out front of that binomial. So if you're stuck on this part, just double check with yourselves. Like ask yourselves, what do you need to multiply? Wait, I needed my pointer. What do you need to multiply 3 by to get 3x? And what do you need to multiply 3 by to get 3? And the answer is x and 1, right? So so once we've factored that out, something magical happens. We can cancel that 3 with that 3, and we're left with this set of binomials. And this is what we want. This is factored form. That's factored. So you know you did it right. If the a value that you put on the bottom of the fraction cancels out, then you did it right. So that's good news. We're going to keep going because remember that this is not just to find factored form, it's to find x-intercepts. So the rest of this is ultra similar to what we did before. We are just using the zero product property because we have two things multiplied to make 0. So we're just going to set ourselves up two equations and say what would make x plus 1 equal 0 and what would make 3x plus 5 equal 0. This one is really similar to the ones before. It ends up being -1. This one, however, has just an extra step, but don't freak out. It's just like when we always solve equations. When you end up with a 3x equals something, you just divide that 3 so you get an x equals, and -5/3 is a perfectly allowable number. It's a fraction, and you will get a lot of fractions when you're doing leading coefficient factoring, but it's perfectly fine. It's allowed. You're allowed to have fractions. And that's it. We did it. The back of this page, feel free to pause if you need more time to write this down. But the back of this page is just a bunch of examples because the best thing to do to get this down is just to do it a billion times. So I won't do all of these with you, but I will do probably the first 3 of this section and then these last 3. So notice the difference in the instructions here. This one says factor, this one says solve by factoring. So on these ones we're just getting it in factored form. On these ones we are going all the way to the answer where you have an x equals something. Okay, so remember that the first thing is to figure out what a times c is. So our a and our c in this equation is 8 and 3. So a times c makes 24. And we're going to make some factor pairs for it. 24 has a lot, actually. It could be 3 and 8, it could be 12 and 2, it could be 4 and 6, it could be 24 and 1. 1, 2, 3, 4. I think that's it. And hang on, I'm double checking something. -12. Why is there no negative? Huh, interesting. I think this one has a typo on it. Oh no, it doesn't. I just did it wrong, that's all. So beware that this one is done wrong on the notes. Anyhow, so we have to get our numbers to add to -10. So 4 and 6, if you make both of them negative, will add to -10. So this is the pair of numbers that we want here. So just remember, we set our two binomials up, and then we put our a value at the beginning of both binomials and then underneath. And then we use our -4 and our -6 to complete those binomials. Now what we're looking for is greatest common factors that we can factor out. So for this binomial here, 8 and 4 have 4 in common, so I'm going to pull out a 4, which would leave us with 2x minus 1. For this binomial, this one also has something in common. There's a 2 in common with 8 and 6. So we're going to need to pull that out as well. So we're going to pull a 2 out front of that one, which leaves us 4x and minus 3. So we pulled out a 2 and a 4. And we still had this divided by 8 down here. So notice that this time, instead of having 1 8, we have a 4 and a 2, which also works, right? Because 4 times 2 makes 8. So canceling these two will cancel the 8, which leaves you with 2x minus 1 in parentheses times 4x minus 3 in parentheses, and that's factored. Like I said, practice makes perfect with this one. If we just do it a bunch of times, you'll get good at it. So this one, remember, A times C is what we're looking for. So A is 5, C is 8. So A times C, what is 5 times 8? 40. 4 and 10, 2 and 20, 5 and 8, I guess. That's how we got it in the first place. I don't know of any more, but this one, we're trying to make it add to our b value still. So our b value being negative 22, we should make both of these negative so that it adds to be negative 22. So we set up our binomials and our fraction. The teacher that I used to teach with for student teaching called this butts on a bench because it looks like butt cheeks on a bench. So if that helps you remember what you're supposed to do, that's good. Anyway, so we have an x here, and our leading coefficient needs to go here, here, and here. And then we have negative 20 and negative 2. Now we're looking for greatest common factors. This one has a 5 in common because 5 and 20, both 5 goes into 5 and 20. So we factor out a 5. What color was I using? Oh, just normal. We factor out a 5, and we're left with x minus 4 times 5 makes 20, so minus 4. And this one, 5 and 2 don't have anything in common, so we can't factor anything out of that one. But it's fine because those 5s cancel. Hang on, that's where I got that 5. The 5s cancel, and we're left with x minus 4 and 5x minus 2. There's factored form for you. On this one, the a times the c gives you a negative 6. 3 times negative 2 gives you negative 6. And we're trying to make it equal. There's an invisible coefficient of 1 right here. So we're trying to make it equal 1. So 2 and 3 is going to be a good option, but 1 and 6 is also available. So we need to make it, it's negative 6, so one of them has to be negative. Let's make 2 negative, so that when we add those, it'll equal 1. Looks good to me. Set up our binomials, our butts on a bench, if you will. And our leading coefficient of 3 goes here, here, and here. Then we have x's, because we need it to equal x squared, and then we have a minus 2 and a positive 3. And look at that, this one has a 3 in common, so we can factor out a 3. So this first one stays the same because there's nothing in common between 3 and 2, but 3 can be factored out of that one, and you're left with x plus 1 because 1 times 3 makes 3. Reverse distributing that one. And it's still all over 3 until we cancel it, and then it's not. So we have 3x minus 2 and x plus 1. That's our factored form for that one. On any of these, if you're feeling like unsure about your answer, you're always allowed to re-multiply these, like redistribute. Let's do that with this. And you should get back where you started if you did it right. So if you're feeling unsure, that's always a good way to check. So I'm going to leave these 3. If you need these examples, they are down below in the notes. Yeah, so feel free to email me if you have any questions about those. I'm going to go down to here, and we're going to practice solving them. So again, same process, except for we just keep going to get a x equals at the end. So our a times our c value, oh, interesting. So notice that this one, 5, 20, and 20, all have something in common. And that's where this step, I'm going to make you dizzy for a second, this step where it says factor out the greatest common factor, here, that's where that one comes in. this one has a greatest common factor already between all of those numbers that we can just divide out to make our lives easier. So I'm going to divide both sides by 5. So this one will be x squared minus 4x plus 4 equals 0. Interesting. And now it doesn't even have a leading coefficient. So we can factor this just like we were doing yesterday. So our c value is 4, and pairs of numbers that make 4 is 2 and 2 and 1 and 4. We need to make it add to our c value, so if we make both of these negative, they will equal negative 4. And we just have x minus 2 times x minus 2. That's our factored form. So we are going to keep going and set up our two mini equations here, x minus 2 equals 0. And then solve. So I'm going to add 2, x equals positive 2. You might notice that these are both the same equation, so we're going to get the same answer. Yeah, that's it. This one I think is also wrong in the notes. I must have been having a rough day. I should probably go through and check the other ones to make sure they're right. Okay, so we're going to keep going. So that one's interesting because factoring out the greatest common factor, or dividing by 5 on both sides, made it so that there was no leading coefficient. So we could just use the process that we learned last time of normal factoring, no canceling necessary. So that's kind of interesting. So let's try this one. First, leading coefficient, greatest common factor, there is none. 12, 5, and 7 have nothing in common. But we can figure out what a times c is. It's negative 84. 7 times 12 is negative 84. So 7 and 12 work. I know that because I just got that from multiplying. So do 42 and 2, 14 and 6. Anyway, there's a lot of options, but we wanted to add to negative 5, which means that we're going to have to choose this option. And again, it's a negative, so we need to figure out which of these need to be negative to make it work. Because they both can't be negative. If we wanted to make it negative 5, we need to make the 12 negative there. So that it'll equal negative 5. Oops. There we go. Okay, here we go. We're setting up our binomials. 12 goes all 3 places, and then we have an x, and then we have a positive 7 and a negative x, negative 12. So you might already be able to tell what's happening here. Look at this. That has something we can factor out so that we can cancel our 12 on the bottom. So we're going to factor out, the first one will stay the same, 12 and 7 have nothing in common, but this one can be factored out, a 12 can be factored out of that one, which is super great because it cancels out this 12 on the bottom, and we're left with 12x plus 7 and x minus 1. Oh, I forgot that we were looking for x values on this one, so we're going to keep going. Equals 0. We're going to set both of these equal to 0 and then solve. X equals 1. That's the nice one. This one's going to be a fraction. 12x plus 7 equals 0. Take away the 7. Then divide by 12. And you get x equals negative 7/12. Beautiful. MathSpace will want it in a fraction, so please don't get decimals for those. Just leave them as they are. Okay, last one. A times c on this one is 3 times negative 4, which makes negative 12. 3 and 4 make 12. 6 and 2 make 12. 12 and 1 make 12. 12 and 1 work. If we make the 1 negative, it will add to 11. So we will set up our binomials, put the 3, the a value, all 3 of those places. This needs an x. This needs a positive 12 and a negative 1. So notice that this one, 3 and 12 have 3 in common. So we're going to pull out 3 out of that one, which makes x plus 4. And this one doesn't have anything in common, so that one will stay the same. There we go. And it's still divided by 3 until we cancel the 3 with that 3 out front. So we're left with x plus 4 times 3x minus 1. Looking for x values, so we're going to keep going. 3x minus 1 equals 0. Add 1. Divide by 3. X equals a nice 1/3. That's as far as fractions go, that one's pretty nice. X plus 4 equals 0. Take away the 4, and x equals negative 4. There we go. So hopefully this one makes sense. Feel free to join our study sessions on Fridays at 11 over Zoom. The link is on my Canvas page. And let me know if you are struggling at any point in this unit. This is a very meaty unit, so that's why we get it over with pretty early.